All right, so for example number 1 from 8.3, so we're solving systems of equations. The most common system of equation used in the real world is cost and revenue. So if I own a company and I make things, doesn't matter what it is. I can make marker caps, right? So to make this little plastic cap, before I make a profit on it, I have to charge per cap. This marker company says, Mr. Adams, can you make me 100,000 caps? I go, sure. I have to charge them a certain amount of money. What I charge them is based on how much it costs to make this cap. The problem is, to make this cap is probably just a couple pennies. But that's not the problem. The problem is that I have to invest in a very expensive mold and very expensive equipment. So I've got to maybe invest $100,000, $200,000 in the mold and the equipment to make these caps for a couple of pennies. So what I do is I come up with a linear equation that represents the cost to make the caps. Then I come up with another linear equation that represents the revenue, how much I make per cap. And then what I do is I solve the system. I look at the two graphs and I solve the system and I realize, oh, I have to make 50,000 caps before I break even. Another one is supply and demand. Supply and demand they're usually two linear equations, and we're looking for an intersection of sorts, and then what goes on beyond the intersection. Okay, so those are two of the most common ones. But anyways, today we're going to learn how to solve a system by elimination. So in this way, sometimes they're rigged up, and then on 8.4 we'll show you how to rig them up to solve by system of elimination. But one thing that I want to point out is that this has a negative 3y and this has a positive 3y. Okay, so notice that if I have a negative 3y and a positive 3y, negative 3y and positive 3y, oops, let me actually write this in here. Positive 3y are opposites, right? So this positive 3y is the opposite of negative 3y. Okay? Well, what happens if I add this thing vertically? Well, keep in mind that 2 plus 1 is 3x, right? But what's negative 3y plus 3y? 0. So when we add those two together, we eliminate what variable? The y, right? Also, 12 plus 6 is 18, correct? Yeah, but it just goes away. How many y's do you have? 0. But that doesn't mean that's the value for y. Is that what you're asking? No. No. We'll have to go back and figure out what y is. So anyways, what we're left with is 3x equals 18. So I got to get the 3 by itself. 3 is being multiplied by x. What's the inverse of multiplying by 3? So we're going to divide both sides by 3. 3 divided by 3 is 1x. What's 18 divided by 3? 6. That's our x value. Now we got to go back and figure out what the y value is. So it doesn't matter which equation you choose. I'm just going to choose this second equation, and wherever there's an x, I'm going to plug in a 6. So I'm going to substitute a 6 for the x variable because according to my math, x equals 6. Now we just solve. So to solve this, what I need to do is subtract 6 from both sides. Oh, dang it, they rigged up this problem. So when you subtract 6 from both sides, you do get 0. And then we have to divide both sides by 3. So we subtract 6 from both sides. And then we divide both sides by 3, and we get y equals 0. That is just a coincidence. Okay? I don't know why they do it that way. Sometimes I look at a problem that the publisher does because kids make these assumptions, right? It's a coincidence. Don't think that through elimination, whatever variable you eliminate will always equal 0. That's just a coincidence that it does. Okay.
I think they just think that we're dumber than we are.
No, I think that they
Or
don't.
no, we're smarter than we are.
Well,
Yeah, that one.
I think that they are used to doing math a lot, and they don't make assumptions that you make when you first learn how to do math. And so, anyways, I'm not gonna bash them.
I'm going.
Any questions on this one? So let me zoom out so you guys could see it. Okay, and I'll give you a second to finish